Okay, hello. Hey, I've been getting a number of questions about the right-hand rules and when to use them and how to use them. And I have been telling you guys and doing a timestamp to go back to the lectures like 121 where we do this, and then also in 122. But I thought somebody requested, why don't I just put it together in one short video here? So this is my attempt to kind of do a summary of these two right-hand rules that cover a lot of different stuff here. So I grabbed the hard copy of the textbook, and it looks like I'm on page 312. It's chapter 11, so it goes back to the mechanics in Physics 121. I'm sure the same is true in the OpenStax book. I didn't look at it, but I know you could also find this on the PDF. But here is what I would call the first right-hand rule. It is a way to get the direction of two cross products. And even though we learned it first in mechanics in 121, that doesn't change the fact that it's, useful this semester. And it's useful next semester in 123 also, anytime we have a cross product. And so you might want to review this part. You could come back here where it says this is the definition, vector C is A cross B. But the right-hand rule is a convenient way of then getting that direction of C. Now, I suppose you could also do I'll call it the mathematical way, and do this determinant of a matrix and figure it out. So, feel free to do that. But this is so easy, so convenient, so quick once you get the hang of it. And it just simply says this. You take your right hand, and whichever one is listed first, which in this case is the A, so down here in the picture there is A, and you point your fingers in the direction of A. So if I point my right hand this way, I'm pointing my fingers that way. Now, once your fingers are pointed that way, okay, so notice as you can rotate your wrist, you can always still leave your fingers pointed in A. So the second part of this is, okay, how do you want me to hold my wrist? So again, fingers in the direction of A. And then you rotate your wrist until closing your fingers, or you might even say your palm, but closing your fingers gets you towards B. Okay? And so in this picture, I would maybe start like this. I'd say, okay, put my fingers towards A. And then maybe rotate my wrist this way, because then here's B, so now I can close towards B. And once you get that, so A's this way, B's this way, then your thumb is the result of C. And so that's what they're trying to say here with this right-hand rule. Now, sadly, in this picture, they show the hand in the closed position. In fact, they close it all the way around, and that's probably not good, because that is more of the picture I want you to see for the second right-hand rule. Okay, but they are trying to say here you are able to close your fingers towards B, and your thumb gives you C. So that's how you get the direction. So any time you see a cross product, in fact, I'll just grab my sticky note here and make the list. In Physics 121, you saw the cross product the first time when it came to torques. And so that's why I'm in chapter 11, and the author's trying to say, hey, let's use this mathematics to calculate torque. In fact, I bet if I just turn the page to the next section, there, that says angular momentum. So maybe they do the angular momentum, because that was the second one I was going to say. Oh, no, here it is. It's earlier. Yeah, okay. So the first thing they do is they say, hey, here's how we can get torque. It's a cross product. So that's why the author then spends all this time talking about how do you do a cross product. Because then the second cross product you see, looks like on page, this be 315, is on angular momentum. Okay, and so I'll put it on the little sticky here. So the direction of the angular momentum is R cross P. So those are the two that you've seen in previous semesters. Now, this semester, we've done quite a few. The first one that comes to my mind is we saw the force on a charged particle moving in a magnetic field given by this equation. So that was chapter 29. In fact, let me jump over here to this section. And so here we are, chapter 29. Here is your author trying to talk about the force. And so look at this picture here. Look how he has in red the velocity and in green the magnetic field. And then the blue is the force. And if you were to take and use that right-hand rule we just talked about, you would put your fingers in the direction of V until, well, yeah, and my fingers could be like this, but then I got to rotate my palm. I better stand up and come over here so I can do it better. But put my fingers in the direction of V, then rotate my palm until I get it towards B, and so now I can close towards B, okay? And which way is my thumb? Up out of the page. And that's what they're trying to show in this three-dimensional version here. So they're kind of repeating it here because this is the first time we see a cross product this semester. And in fact, that's why I thought, hey, let's look at the top of page 811 here. Here's where he reviews this right-hand rule. So he did it already, as I said, back here in chapter 11, but now he is redoing it because this might be the next time you see it. And so we go all the way from page 300 and something to 800 and something. So we don't see it for about 500 pages, and then we get back to this cross product. So it's what he's trying to show here. Now again, for better or worse, he's showing the hand and the fingers already closed, and I think it would be better if he kind of showed a kind of a sweeping motion here. They could show like a full picture here and then a grayed out position here, I suppose. But he has it all the way like that. And the reason I'm not crazy about that one is because that's the second right-hand rule I want to talk about. And so I like this position, the thumbs up position for the second right-hand rule. So I'm closing it. But you can see in this picture, he's putting his fingers in the direction of V. And so his fingers would be before he closed it. And then he's adjusted his wrist so his fingers can close towards B. That is, his palms towards B, and his thumb is giving him the up direction. Now, he also says, and maybe this is more harmful than useful, that, there's other ways of listing three dimensions, and he says you could do this if you wanted. And he talks about another option. But let me hold off on that. I'm just going to say I don't even want to bring that up. I think we should you pick one and stick by it. So, you could do this one, and that's useful. And I know one of you asked a question about, well, I'm confusing it with the one in my math class. Now, I don't know what you use in your math class, but if you're doing, mine in the math class, that would be more helpful than if you do this model. But let me encourage you to look at this model if you're doing this model in your math class. Both of them are equivalent. You just need a three-dimensional vector set, and it's just, the x, y, z axis, so you need 3 dimensions. So B is kind of a different one. So I'm going to hold off on that one and say don't think about that. But what I wanted to point out is do not call this the second right-hand rule. That is not what I'm calling the second right-hand rule, okay? And so the first one here is how you find a cross product. Well, let me keep going with this list, because immediately after this one, which is the force on a moving charge in a magnetic field, we said there would be a force on a bunch of charges, a current moving in a magnetic field. And so there's another cross product. So all of these you would solve the same way. You would put your fingers in the direction of the first one, which would be R, V, or L. And then you would close your fingers towards the second one. And in this case would be F, or it would be P for momentum, or B for magnetic field. So all the cross products are done the same way. Fingers in the front one, rotate your wrist so you can close towards the second one. Thumb is the direction of the third one, which in this case would be torque, angular momentum, force, and force. I bet if I turn the page, I'm going to then quickly find how far I have to go before the author gets into the force. There it is. Page 8. What is this? 820. And there it is. There is another cross product there. Okay. And if we keep going, I know we will soon get to two other cross products. One is the torque on a loop of wire, and so you do the magnetic moment and the magnetic field. So your fingers would go in the direction of that one, and then you would close it. So you would adjust your wrist so you can close your fingers or put your palm in the direction of that one, and then the torque would be that direction. And the last one I can think of is the B up sub art, which said a little bit of force coming from a little bit of field. And so the first part I'll just write down mu naught 4 pi, and then the current I. But the cross product is this. It is the direction of the current crossed with the r hat vector and then divided by r squared. But there's another cross product. And so you would put your fingers in the direction of the ds, you would close your hand towards the r hat, and then your thumb would give you the direction of the df. So it looks like you have seen, if I'm remembering them all, over the course of Physics 121 and now this semester, 6 cross products. And all of them then are done essentially the same way. There's the fifth one I listed. And the sixth one must be the start of chapter 30. Yep, there it is. And so at the top of 30, there it is. So there's another cross product. So I'll say it again. All of these involve the right-hand rule number 1. In fact, that's how we got the magnetic field coming out, right? You put your fingers in the direction of ds. So put my fingers in the direction of ds. Rotate my wrist so I can close towards r hat. And then my thumb would be in the direction of the cross product. All right, so that's the first right-hand rule. And so again, anytime you see a cross product, use that one. So I like to call that right-hand rule number 1, or the right-hand rule for finding the direction of a cross product, okay? And that's, again, one that you would see in a math class. Now, the second one you wouldn't see in your math class. It's strictly about currents and magnetic fields. It is really kind of a result of this. So right-hand number 2, you could say it's just the result of this after you do an integral. So in some sense, you could say, I don't need it. But it is so useful that I encourage it. So let's talk about right-hand rule number 2. And your author begins right-hand rule number 2 for the first time, looks like right here, on page 813. And let me explain right-hand rule number 2. Right-hand number 2, you just have the right hand in the thumbs up position. You don't do any of this, put your fingers and close your fingers. There's no motion to your hand. And so maybe in some sense it's easier to explain than on a picture that way. You just hold your hand in a thumbs up position. Now, your author has it where his hand isn't quite as tight as a thumbs up. So whichever way you want, I suppose, because he wants you to be able to look at your fingers and your thumb. But here's how you do right-hand rule number 2. You hold your right hand in this kind of thumbs-up position, and then you look at the current you have. And your current will either be looping around in a circle, and if that's the case, use your fingers to represent the current, or the current will be in a straight line. And if that's the case, then use your thumb as the current. So I wish I could say always use your fingers for the current, but that's not the case. Sometimes your fingers are the current, and sometimes your thumb is the current. So that's why number 2 can be a little confusing. But the key to remember then is to look at the shape of the current. So, all right, so in this case, the shape of the current is this ring, and that would match the shape of my fingers. So which way is the current going? Well, as looked from above, looking down on it, this would be in a counterclockwise direction. So hold your right hand so your fingers would match that. And I say your fingers match it with the kind of the end of the finger being the pointer, so it goes around this way. See, because if I held it this way, I would say that's how I would do it if I was doing a counterclockwise current, because my fingers are pointing this way in a clockwise direction. Okay, but this one looks like this, where my fingers, when you look down from above, go in a counterclockwise direction. So if this is the current, then your thumb becomes the direction of the field. So they are saying this would be the direction of the field, which in this case is the magnetic moment. And so there it is. Put your fingers in the direction of the current, and this would give you the field. Now, let me be careful here, because your fingers are not always the current. Sometimes your thumb is. But in that case, if your thumb is the current, then your fingers are the field. So the best way to describe rule number 2 is to say, match your fingers or your thumb with your current, and the other one will give you the field. So in this case, my fingers tend to match the current. Good. So I'll put my fingers to match the current, and so my thumb gives me the field. Now, the reverse of this, which I would also call right-hand rule number 2, is what your author is trying to show on this page, page 840. And he's got this right hand. And so let me just do the thumbs up again. And let's look at the current. See, notice the current is a straight line. So the first thing I would ask myself is, my thumb or my finger is going to represent the current. Remember, my thumb is straight, my fingers are curved, and I have a straight current. So my thumb would be the current. And that means my fingers would be the field. And so as I match my right hand in this picture, you will see that the thumb is in the direction of the current, and then the fingers wrapping around, and so shown in green here, is the direction of the field. So the field would make a circle when the current is a straight line, which is the reverse of what I just showed you. When the current is in circles, the field is a straight line. So that's why these play that role. Hope that helps, but those are the 2 right-hand rules.